from the online audience?
Okay, so popular question is how to figure out in a systematic way the nonlinear transformations instead of looking at the data.
Okay, so I said that the nonlinear transformation is a loaded question, and there will be two steps in dealing with it. So I will talk about it a little bit more elaborately at the beginning of next lecture, and then we are going to talk about the guidelines for choice and what you can do and what you cannot do after we develop the theory of generalization, because it is very sensitive to the generalization issue. And that should not come as a surprise, because I can see that, okay, I can take the input, which is, let's say, two variables corresponding to two parameters, and I want the transformation to be as elaborate as possible in order to be, to stand a good chance of being able to separate them linearly. So I'm going to go all out. I'm just going to keep getting nonlinear coordinates, x1, x1 squared, x1 cubed, x1 squared, x2, e to the x. I'm just that, just go on. Now, at some point, you should smell a rat, because you realize that, okay, I have this very, very long vector and corresponding number of parameters, and generalization may become an issue, which it will become an issue. So there are guidelines for how far you can go, and also there are guidelines for how you can choose them. Do I look at the data and figure out what is a good nonlinear transformation? Is this allowed? Is this not allowed? What the ramifications are? All of these will become clear only after you look at the theory part.
Okay. There's a question about slide 15. So regarding the expression of E in, so how does the in-sample error here or the out-of-sample error would relate to the probabilistic definition of last time?
Okay. Here we dealt only with the in-sample error, okay? So we decided on E in, and in general in learning, you only have the in-sample error to deal with. You have on the side a guarantee that when you do well in sample, you will do well out of sample. So you never handle the out of sample explicitly, you just handle the in sample and have the theoretical guarantee that what you are doing will help you out of sample. Now, the error measure here was a squared error, okay? Therefore, when you define the in sample error, you get the squared error and average it. And when you define the out of sample error, it's really the expected value of the squared error. Now, in the case of the binary classification, the error was binary. You're either right or wrong. So you can always define the in-sample error as also the average of the question, am I right or wrong on every point? So if you are right, you get, there's no error, you get 0. If you are wrong, you get 1. So you ask yourself, what is the frequency of ones in sample? And that would give you the in-sample error. The expected value of that error happens to be the probability of error. That's why we simply, without going into expectation and in-sample average versus out-of-sample expected value, in the case of classification, we simply talked about frequency of error and probability of error. Not because they are different, but just because they are simple to state. But in reality, the aspect of them that made them qualify as in-sample and out-of-sample is that one of the probability is the expected value of an error measure that happens to be a binary error measure, and the frequency of error happens to be the average value of that error measure.
So you showed us very nice graph with negative slope about dependence of future income and...
just unintentional. I didn't think of the income at the time I drew the graph. So any implication that you should really do worse in school in order to gain more money, is, I disown any such conclusion.
Okay, but you mentioned the example of determining future income from graded point average, or at least finding some correlation. So the question I'm interested in is, where can we get data?
Okay, I mean, you can get, obviously the Alumni Association of every school keeps track of the alumni, and they send them questionnaires, and they have some of the inputs is how much money they make. I mean, there are a number of parameters. So there will be a number of schools that have that, and actually this is actually used. So, if you realize that something is related to success or some things, you can go back and revise your curriculum or revise your criteria and whatnot. So the data is indeed available. If that's a question, yeah.
I mean, it's available in principle, but can we get it?
Oh, we get it, okay. So I thought it was generic we. I don't, okay, so obviously the data will be anonymous after a while. You'll just get the GPA and the income without knowing who the person is. It will be, you are dependent on the kindness of the alumni associations at different schools, I guess, okay? Or maybe there are some available in public domain. I have not looked, okay? So my understanding is that you want to run linear regression, see what happens, and then focus your time on the courses that matter. That's the idea now? That's your feedback? Okay.
Okay, so technical question, why is the W0 included in the linear regression? So there's a confusion about this. And also into that point, like, so what do you do specifically in the binary case? How do you incorporate that +1s and -1? There's people asking about this.
Let me ask one at a time. Let's talk about the threshold first, why the threshold is there, right? So let's look here. If you look at the line here, this is the linear regression line. The linear regression line is not a homogeneous line. It doesn't pass by the origin. If I told you that you cannot use a threshold, then the constant part of the equation goes away, and the line you have will have to pass through the origin. Can you imagine if you're trying to fit these with a line? I mean, obviously, it would be down there if you have the negative slope, or if you want to pass through the points up there. So obviously, I need the constant in order to get a proper model. And in general, there is an offset depending on the values of these variables, and the offset is compensated for by the threshold. So that's why we need the threshold for linear regression. What is the second question?
So in the binary case, so when you use y as +1 or -1, so why does that just work, basically?
Okay, well, if you apply linear regression, you have the following guarantee at the end, okay? The hypothesis you have has the least squared error from the targets on the examples. That's what has been achieved by the linear regression algorithm. Now, the outputs of the example is being +or -1. We can put that together with the first statement, and then we realize that then the output of my hypothesis is closest to the value +1 or -1, okay, with a mean square error. The leap of faith is that if you are close to +1 versus -1, then the chances are when you are close to +1, you are at least positive, and when you are close to -1, you are at least negative, okay? If you accept that leap of faith, then the conclusion is that when you take the threshold of the value of the signal from linear regression, you will get the classification right, because positive will give you +1, negative will give you -1. This is not quite the case, because in the attempt to numerically replicate all the points, the signal for linear regression can become, let's say, as I mentioned, +7 for some points, and -7 for another point, and the linear regression is trying to push the W, which is what will end up being the boundary, in order to capture that numerical value. So in attempting to fit stuff that is irrelevant to the classification, it may mess up the classification. And that's why the suggestion is don't use it as a final thing for classification, just use it as an initial weight, and then use a proper classification, something as simple as the pocket algorithm, in order to fine-tune it further, in order to get the classification part without having to suffer from the numerical angle.
So also on that, does it make a difference what you use? Is it +1, -1, or something else?
Okay. If it's plus something and minus the same thing, it's a matter of scale. If it's plus and minus and not symmetric, it will be absorbed in the threshold. So it really doesn't matter. It will just make things look different.
Okay, so regarding the first part of the lecture, so how do you usually come up with features?
Okay. The best approach is to look at the raw input, okay, and look at the problem statement, and then try to infer what would be a meaningful feature for this problem. For example, the case where I talked about the years in residence, it does make sense to derive some features that are closer to the linear dependency. There is no general algorithm for getting features. So this is the part where you work with the problem and you try to represent the input in a better way. And the only catch is if you look at the data in order to try to derive the input. That is, there is a problem there that will become apparent when we come to the theory. But the bottom line is that if you don't look at the data and you study the problem and derive features based on that, that will almost always be helpful. If you don't have too many of them, if you have too many of them, then it starts becoming a problem. But something, first order, usually when I get a problem, I look at the data, and I probably can think of, less than a dozen variables that will be helpful. And I put all of them, and usually a dozen variables in this case doesn't increase the input space by much. These are big problems, and so I don't suffer much from the generalization issue.
So added to that, a short clarification. So the nonlinear transformations, they become features. Yeah.
So the word feature, we are going to use, there's a feature space which is called Z, and anything that you take the input and transform it into something else, this will be called feature, and features of features will also be features, okay? So if you take, for example, the classification of the digits, we had the pixel values, that's the raw input. And then we had the symmetry and the intensity. These were features. If you go further and find nonlinear transformations of those, these will also be called features. A feature is any higher level representation of a raw input.
So another question is, so how does this analysis change if we cannot assume that data are, or if they are correlated, if they're not independent?
Not clear about the question. So there is really, okay, so I think I get, so probably when we get the inputs, the question is independence versus dependence, and the independence was used in getting the generalization bound. That's probably the direction of the question. The independence was from one data point to another. So I have capital N inputs, and I want these guys to be generated independently according to a probability distribution. If they were originally independent, and I transformed one of them and transformed the other, the independence is inherited. There is no question of independence between coordinates of the same input. The independence, there was a question of the independence between the different inputs.
So the different inputs.
Different input points.
So another question is, so are there methods that use different hyperplanes and intersections of them to separate data?
Correct. The linear model that we have described is the building block of so many models in machine learning. You will find that if you take a linear model with a soft threshold, not the hard threshold version, and you put a bunch of them together, you will get a neural network. If you take the linear model and you try to pick the separating boundary in a principled way, you get support vector machines. If you take the nonlinear transformation and you try to find a computationally efficient way of doing it, you get kernel methods. So there are lots of methods within machine learning that build on the linear model. The linear model is somewhat underutilized. It's not glorious. And it's not glorious, but it does the job. The interesting is that if you have a problem, there is a very good chance that if you take a simple linear model, you will be able to achieve what you want. You may not be able to brag about it, but you are going to do the job. Okay? And obviously, the other models will give you an incremental performance in some cases.
So a question getting a little bit ahead. So how do you assess the quality of in and E out systematically?
Okay, this is a theoretical question. En is very simple. I have the value of En. I can assess its value by just looking at its value. I can evaluate it at any given point. And this is what makes the algorithm able to pick the best in-sample hypothesis by picking the one that has the smallest in-sample error. The out-of-sample error I don't have access to. There will be some method described after the theory that will give us an explicit estimate of the out-of-sample error. But in general, I rely on the theory that guarantees that the in-sample error tracks the out-of-sample error in order to go all out for the in-sample error and hope that the out-of-sample error follows, which we have seen in the graph when we were looking at the evolution of the perceptron, and the in-sample error was going down and up, and the out-of-sample error was also going down and up, albeit with a discrepancy between the two, but they were tracking each other.
So here's a question that's kind of a confusion. So if you want to fit a polynomial, is this still a linear regression case?
Correct, because right now, let's say we have a single input variable, x, like the case I gave. Okay, so you have x and y. Okay, now you have a line. If you use the nonlinear transformation, you can transform this x to x, x squared, x cubed, x to the fourth, x to the fifth, and then fit a line to the new space. Okay, and the line in the new space will be a polynomial in the old space. So this is covered through the nonlinear transformation.
So what is the relation between linear regression least squares with maximum likelihood estimation?
Okay, when you look at linear regression in the statistics literature, there are many more assumptions about the probabilities and what the noise is, and you can get actually more results about it. Under certain conditions, you can relate it to the maximum. Like you can say, okay, Gaussian goes with the squared error, and in this case, minimizing it will correspond to maximum likelihood. So there is a relationship. On the other hand, I prefer to give the linear regression in the context of machine learning without making too many assumptions about distributions and whatnot, because I want it to be applied to a general situation rather than applied to a particular situation. As a result of that, I will be able to say less in terms of what is the probability of being right or wrong. I just have the generalization from in-sample and out-of-sample, but that suffices for most of the machine learning situation. So there is a relationship, and it's studied fairly well in other disciplines, but it is not of particular interest to the line of logic that I'm following.
So a popular question is, can you give at least a set of usual nonlinear transformations used?
Okay, there will be many. I mean, when we get to support vector machines, we will be dealing with a number of transformations, some of them polynomial, like one we mentioned. One of the useful ones is referred to as radial basis functions. We will talk about that as well. So there will be transformations, and the main point is to be able to understand what you can and what you cannot do in terms of jeopardizing the generalization performance by taking a nonlinear transformation. So after we are done with that theory, we will have a significant level of freedom of choosing what nonlinear transform we use, and we'll have some guidelines of some of the famous nonlinear transforms. So this is coming up.
So I think you already answered this question last time, but again, someone asks, is it impossible for machine learning to find the pattern of a pseudo-random number generator?
Well, okay, if it's pseudo-random, then in principle, if you get the seed, you can produce it. But the way it's usually used is you use a pseudo-random number, and then you take a few bits and have them as an output for different inputs. So just looking at the inputs and trying to decipher it, it's next to impossible. So it's a practical question. I mean, philosophically, yes, you can. Practically, it looks random for all intents and purposes.
So what are the different treatments for continuous responses versus discrete responses in, I guess, in
yeah.
Y, I guess?
Well, I mean, obviously, this is dictated by the problem. If someone comes and they want to approve credit, etc., I'm going to use a classification hypothesis set. If someone wants to get a credit line or something else, then I will have to use regression. So it really is dependent on the problem. And the funny part is that real numbers look more sophisticated, yet the algorithm that goes with them, which is linear regression, is much easier than the other one. The reason is that the other one is a combinatorial, and combinatorial optimization is pretty difficult in general. So the answer to the question is that it depends on the target function that the person is coming up with. And when there is sort of cross-fertilization between the techniques, it's just a way to use an analytic advantage from one method to give the other one a jump start, or to give it a reasonable solution. But it's a computational question. The distinction is really in the problem statement itself.
Can you say what makes a nonlinear transformation good?
Okay. I will be able to talk about this a little bit more intelligently after the theory. Okay. I would like to emphasize that the theory part will be very important in giving us all the tools to talk with authority about all the issues that are being raised. So there is a reason for including the theory before we go into more details. This lecture was meant to give you just a little bit of standard tools that you can use, and if you look at it now, you can use for many applications and many data sets, because now you can deal with non-separable data, you can deal with real valued data, and you can even deal with some nonlinear situations. So it's just a sort of a toolbox for you to get your hand wet, and then things will become more principled when we develop more material.
Yeah, I think that's it.
Okay, that's it. So we will see you on Thursday.